A building's ability to withstand seismic activity is one of the greatest challenges in civil engineering. Tall structures must resist not only the force of gravity, but also strong winds and, in certain regions, major earthquakes. In response, some skyscrapers have adopted clever and relatively discreet solutions to ensure structural stability. One of the most impressive examples can be found at the top of Taipei 101 in Taiwan, where a massive metal sphere known as a tuned mass damper is installed. This sphere, besides sparking visitors' curiosity, plays a key role in absorbing vibrations, helping the building stay upright during tremors and extreme winds. Before we dive into why this sphere is so essential, it's worth clarifying a few things about the nature of earthquakes and how buildings behave during them. The Earth is dynamic. Tectonic plates move, generating stress and releasing energy in the form of seismic waves. When these waves reach man-made structures, they produce horizontal and, to a lesser extent, vertical oscillations that can compromise structural integrity. In earthquake-prone areas, engineers must find ways to absorb or dissipate this energy to prevent collapse. That's where vibration control technologies, like the tuned mass damper, come into play. The term tuned mass damper, known as TMD, refers to a device designed to move in the opposite direction of a building's natural vibration. In other words, when a building sways one way, the device shifts the other, canceling out much of the motion. In the specific case of Taipei 101, the TMD is a giant metal sphere, weighing hundreds of tons, suspended by steel cables and resting on shock absorbers. It's not just there for show, its function is crucial for both safety and the comfort of the building's occupants. Although wind is a more frequent phenomenon than earthquakes, both generate lateral forces that can cause a very tall structure to sway significantly. Imagine a building that's 1,300, 1,600, or even 2,000 feet tall. With a tip so far from the ground, horizontal swaying can be enough to cause motion sickness, not to mention structural damage if the energy isn't controlled. That's why solutions like the one used in Taipei 101 help keep the building steady, reducing lateral movement caused by strong gusts or moderate seismic activity by up to 40%. Choosing Taiwan as the site for a skyscraper like Taipei 101 was strategic from both a commercial and symbolic standpoint, but it brought major engineering challenge. The region is known for significant seismic activity, so constructing one of the tallest buildings in the world required highly advanced technological approaches. Among the many solutions adopted, the use of a TMD stands out, with a design that's as simple as it is effective. Generally, a TMD consists of a counterweight, in this case the massive metal sphere, a support system, cables or columns, and damping mechanisms, hydraulic parts, or energy-dissipating materials. What matters most is that the pendulum mass is tuned to the building's vibration frequency, allowing it to respond at the right moment to counteract swaying. To give you an idea, this gigantic sphere in Taipei 101, often nicknamed the damper ball, has a diameter of about 18 feet and weighs roughly 1.45 million pounds. That size is no accident. It needs enough mass to influence the dynamics of a skyscraper that rises more than half a kilometer into the sky. When an earthquake or strong wind hits, the tower tries to sway at a certain natural frequency. If nothing were done, those vibrations could intensify to the point of becoming uncomfortable or even unsafe. But with the sphere moving in the opposite phase, the vibration energy is partially dissipated by the dampers and the elastic components of the support system. One of the most interesting aspects of the Taipei 101's TMD is that it's open to public view. In many buildings, these systems are hidden away in service areas, off limits to visitors. But in Taiwan, there's a strong educational and marketing effort built around this device, which tourists can see on some of the upper floors. It's a way to show, quite literally, that modern engineering isn't just about reaching new heights, but also about ensuring safety and comfort for occupants. And of course, it's fascinating to witness how such a massive sphere, almost like a suspended work of art, moves to stabilize an entire colossus of concrete, steel, and glass. To better understand why the sphere is crucial during a seismic event, it helps to think about the concept of resonance. Resonance is when a system vibrates more intensely in response to stimuli that match its natural frequency. Buildings, much like guitar strings or crystal glasses, have their own natural frequencies. If the energy from an earthquake, which arrives in multiple frequencies, but especially one that may match the buildings, hits the same frequency range, the structure can sway with dangerously large amplitudes. The TMD adds an extra mass that, by moving in the opposite direction, breaks this resonance, significantly reducing vibration peaks. That way, even if the quake's frequency aligns with the buildings, the potential damage is much lower. In the specific case of Taipei 101, which held the title of the world's tallest building from 2004 to 2010, one of the major concerns was typhoons, which are quite common in Taiwan. These weather events bring strong, sustained winds that can cause a high-rise to sway uncomfortably. The TMD also comes into play here. By swinging in opposition to the wind-induced motion, it reduces the feeling of swaying. As a result, residents and visitors in the building experience a much greater sense of comfort without that unsettling sensation often felt in very tall environments. The idea of using a tuned mass damper in buildings didn't originate with Taipei 101. Other major structures like the John Hancock Tower in Boston, which uses devices to reduce wind effects, or the Citicorp Tower in New York, famous for its emergency structural fixes, also implemented damping system. However, Taipei's design stands out for both the public visibility and the sheer scale of the device. And increasingly, as buildings grow taller, this type of technology is expected to become standard in large-scale construction. Beyond buildings, structures like suspension bridges can also benefit from similar concepts. The goal is always to prevent resonance from intensifying, since repeated and amplified movements can lead to material fatigue, cracks, structural shifts, and in extreme cases, collapse. Some well-known examples of resonance-related failures can be found in bridges, like the Tacoma Narrows Bridge, which collapsed in 1940 due to relatively moderate winds that triggered severe vibratory motion. While that bridge didn't use a TMD, we now know that vibration control devices and aerodynamic designs can prevent such drastic events from happening again. For those visiting Taipei 101, seeing this giant sphere is one of the highlights of the experience. On some of the upper floors, there are windows and walkways that let you view the suspended metal sphere up close. There's even a character called Damper Baby, a playful mascot version of the TMD. Though lighthearted, it helps bridge the gap for the general public to understand what might otherwise seem like an abstract engineering solution. The idea of a pendulum weighing hundreds of tons swinging in sync with the tower feels almost magical. But with just a bit of understanding of physics and dynamics, it becomes clear that it's actually a straightforward and reliable way to handle extreme events. Another important point worth highlighting is the need for a strong base in structure to support the weight of the TMD. After all, it's not just about placing a ball at the top of a building. Engineers have to carefully calculate load distribution so that the floor housing the TMD can safely support it without compromising communal spaces or critical equipment in the skyscraper. This involves specially sized steel beams, fastening systems, and cables that must be regularly inspected. All of this ensures that during an earthquake or storm, the sphere won't detach and cause a disaster. It's a project that demands expertise in structural analysis, vibration dynamics, and material science. We also can't ignore the cultural and touristic impact the TMD has had on Taipei 101. Today, it's practically an icon within the building. Many visitors say the main attraction isn't just the panoramic view from the observatory, but also getting to see the giant damper sphere. This marks a shift in mindset. Engineering solutions used to be hidden and rarely part of a tourist experience. Now they're showcased as both attractions and demonstrations of safety. This kind of transparency helps the public understand, at least on a basic level, how engineering tackles real-world problems. Speaking of engineering, it's interesting to note that this kind of technology requires in-depth study of structural dynamics, involving heavy use of computer simulations and wind tunnel testing. Before construction, scaled models of Taipei 101 were tested to estimate how the building would respond to typhoon winds and potential earthquakes. A wide range of scenarios were analyzed, from minor tremors to extreme events. These tests aimed to determine the optimal parameters for the TMD: mass, stiffness, type of damper, and even its exact placement within the building, all to ensure it's properly tuned not only to the building's primary vibration frequency, but also to secondary vibration modes. In the case of very strong earthquakes, a building structure also needs to have ductility, that is, the ability to deform without breaking, to ensure that even under extreme conditions, columns and beams bend in a controlled way rather than snapping in a brittle failure. The TMD doesn't solve everything on its own. It's part of a larger system, a robust setup of deep foundation, concrete and steel cores, and beams designed to redistribute stress. But without a doubt, the TMD adds an extra layer of safety by reducing the strain on these structural elements. In areas without seismic activity, Buildings can use other types of passive control systems or even active damping systems where sensors detect motion and hydraulic or electric actuators adjust the position of masses. But those are usually more complex and expensive. The giant sphere in Taipei, on the other hand, is a passive solution, which makes it reliable and relatively simple. It doesn't rely on motors or complex algorithms to adjust, since it responds naturally to oscillation. Another interesting point is how the local culture embraces this solution. In Taiwan, there's a certain pride in showcasing the country's engineering sophistication, even if the project involved international teams. The message is clear: we have the technology to build something that symbolizes economic power, while also providing safety for those who live and work inside the building. For residents and visitors alike, there's peace of mind in knowing that during an earthquake or storm, this device is ready to soften the impact. It's worth highlighting how the basic operation of the giant sphere reflects fundamental physics concepts like action and reaction, energy conservation, and harmonic system, showing that behind a skyscraper, there's a heart made of steel and cables protecting it from nature's fury. At the same time, it's important to make it clear that this isn't an unbreakable shield. In the case of an extremely powerful earthquake, the building can still suffer serious damage, but the risk of collapse drops significantly since a large portion of the seismic energy is dissipated. It's also worth pointing out that Taipei 101 has already faced both earthquakes and typhoons since its inauguration, and the TMD's effectiveness has been proven not only through instrumental measurements, but also through the experiences of those inside the building. On windy days, sensors record how much both the building and the sphere move, and it's been shown that total sway can be reduced by up to half depending on wind intensity. For occupants, this means they might feel only a light tremor during more severe conditions, instead of a dramatic sway that could cause discomfort or panic. Moreover, this damping solution isn't a disposable item that needs to be replaced after each extreme event. The TMD is designed to operate continuously throughout the building's lifespan, as long as it undergoes regular inspections. The damping materials can wear over time, but they're maintainable. The cables holding the sphere are also periodically checked to prevent fatigue, so there's a whole system of monitoring and preventive maintenance in place to ensure that when the protection is really needed, it's fully ready to do its job. Taipei 101 was inaugurated in 2004 and has since solidified its status as a landmark that blends aesthetics with smart engineering solutions. The building is recognized worldwide not only for its height, but also for its bold use of seismic protection feature. The roof was designed to withstand winds exceeding 134 miles per hour, crucial in a region frequently hit by typhoons. Deep anchoring and foundations ensure that loads are safely transferred to the ground. And at the top, the famous sphere provides precise control over swaying, reducing risks, and increasing comfort. At the end of the day, the big takeaway from Taipei 101's Tune Mass Damper, for engineers and enthusiasts alike, is that sometimes the solution to massive problems can be relatively simple, as long as it's precisely engineered. A suspended sphere weighing hundreds of tons wouldn't prevent a catastrophic collapse on its own if the building were poorly designed. But combined with other safety features, it significantly reduces the impact of lateral forces from earthquakes and wind, ensuring the stability of one of the tallest skyscrapers on the planet.